Do you think static camera shots are boring? The brilliant James Bruton did a great video on building a camera motion control rig that started with that very question, to which I think the answer is definitely, sometimes, probably. He went on to build a wheeled robot camera system. In my videos, I tend to do fewer headshots, shots like this one, mainly because I think it's probably the least exciting part of my video. I do, though, tend to have lots of static shots of breadboards, components and builds. Sometimes it's hard to quite see what I've done from a single angle. So what if they were animated? Not just bouncing around the screen like ping pong? What if the boards were rotating in front of the camera and stopping for the final close-up shot? Bottom line up front, this is a Raspberry Pi Pico project to control a video turntable and lighting rig. I'm going to have a small user interface to see the parameters using some switches and rotary encoders with an OLED screen so that I can see what I'm doing. Then a 3D printed turntable powered by a 28BYJ48 stepper motor and a ULN 2003 driver chip, using a Hall sensor to detect the start position. The light rig to control the brightness and colour of my video area is going to be using WS2812B LEDs. This is version 1 of the project with a turntable to control speed, position and illumination. I have a plan to add to this the camera controls too. Right now the camera is just a static camera on a tripod in front of the turntable. What if the camera could pan and tilt though? It could zoom into the objects or drop down onto them. I have a robot arm lying around and plan to try out that with a camera in a later video. Today though, it's about the turntable. This video is sponsored by PCBWay, who helped me out with the manufacturing of the PCB for this video. More about PCBWay later. Let's talk about the electronics this project needs. To move the turntable, I'm going to use a stepper motor, so I can move it to a specific position and turn it at a specific speed. I'm going to use the 28BYJ48 very cheap stepper motor with the ULN 2003 Darlington array. I picked up a pack of 5 motors and controllers for £10 off of Amazon. I've done a more in-depth video on these stepper motors and controlling them on YouTube. I'll link to that in the description. To turn to a specific angle, I need to know a start position of the turntable. I'm going to use a Hall sensor to do this. Hall sensors detect magnets, so sticking a magnet on the underside of the turntable will let me know the 0 position of the turntable. I'm using the A3144 sensor. I've done an in-depth video on this one too. The lighting of my video studio is going to use the WS2812B LEDs. These are serially controlled RGB LEDs. You get them single, on strips or in shapes. I've used them in a number of other projects and have an in-depth guide on my Pico microprojects course in C++ on Udemy. I'm going to use some strips for lighting here. I can get 23 LEDs in each run across my little tabletop photo studio. I'm going to drive these LEDs at 5 volts and therefore I need to do some signal level changing of the 3.3 volts from the Pico's GPIO pads. A quick hack for doing this is to use a 7400 quad NOR gate chip and have 2 NOR gates in series. These trigger fine at the 3.3 volts level produced by the Pico and give a clean 5 volt signal output. I'll use some single pole, single throw switches for input to start and stop the turntable, a rotary encoder for editing the configuration, and OLED screen to show the controls. I will put a full schematic, both in the KiCad format and a PDF, up on the GitHub repository for this project. Stepper motor is being driven by the ULN 2003 Darlington driver. I'm not going to use the little driver board but put the ULN 2003 directly on the PCB. Just like the driver board, I have a decoupling capacitor around the power to the ULN 2003. The A3144 sensor is going to be a separate board underneath the turntable. Like I did in my previous video, this sensor is powered by 5 volts and with an output pulled up to 3.3 volts to drive the input. It is key that I only do pull this up to 3.3 volts, as this will be using GPIO 28, which is not 5 volt tolerant. I've put an LED on GPIO 2 as a pulse or turn on LED to see things are working. The rotary encoder will be on GPIO 2, 3 and 4. I've used some capacitors to smooth out some of the bouncing and will use a polling strategy. I have an in-depth tutorial on using mechanical rotary encoders with the Pico in my Pico micro projects course on Udemy. The 4 switches are connected in pull-down mode to GPIO 6 to 9. Again, more on reading switches in the Pico micro projects C++ course. Finally, the OLED display will connect to J1 and will use GP14 and 15 as the I2C interface to our Pico. The WS2812B LEDs will use the 7400 NOR gate to be a unidirectional level shifter for the 5 volt control. I have enough NOR gates to drive 2 separate WS2812B LED strips, though I'm only going to use one for the project. I've designed up a second channel for potential future use. Driving a lot of WS2812B LEDs means we'll need a reasonably beefy power supply, so I'm going to put a fuse on the power supply and a 1000 microfarad capacitor over the supply. This is to protect the Pico from brownouts when the LEDs go from off to full on. I've built a number of projects using prototype boards where one connects up the circuit from scratch with solder. Boards like this fairly simple Raspberry Pi hat. They take a huge amount of fiddling around to put together and are time consuming, especially when you make mistakes and have to desolder stuff. So much easier to get skilled team like the team at PCB Way to manufacture the PCB for me. In a week, I can have these fabricated and shipped to me. Look how clean the board is compared with a prototype board. I save so much time too in soldering the components up onto the board. So thank you PCB Way for providing the board for this project. This video is sponsored by PCB Way. PCB Way are a PCB fabrication and build service who also provide 3D printing, CNC, sheet metal fabrication and injection molding services. Check out their services and try out the friendly service from PCB Way on your projects too. The physical design I've done in OpenSCAD and 3D printed. The turntable top has an internal gear underneath it, and the spur gear from the motor drives this. The spur gear itself sits on the stepper motor. The motor mount is separated to make printing easier and allow the motor position to move a bit to adjust to a perfect position for that spur gear. The turntable attaches to the base through a large bearing. This is a nice and snug fit. Then a sensor arm for the hall sensor to detect a magnet, which is just stuck onto the underside of the turntable. I'm lucky enough to have my own 3D printer, so this was just a few hours to build in PLA. If you don't have a 3D printer, remember my friends at PCB Way also do 3D printing and could print this model in PLA, ABS or nylon. The software for this project is very straightforward. I've written this all in C++ using Pico SDK. I use C++ rather than just C so I can encapsulate the design into objects. The data and functions are closely connected, with clean interfaces between objects. This helps me speed up my development. To further help separate out the components, and because of the active nature of controlling of them, I'm using FreeRTOS. So the user interface display on the OLED screen is a task, and so is the motor control and the polling of the rotary encoder. I've used Forsaken NGS's Pico LED library to drive the WS2812B LEDs and the Pico SSD 1306 library to drive the OLED display. I've already done videos talking about the GPIO waggling needed to control the 28BYJ48 stepper motor. I'm doing that within a FreeRTOS task, so the motor can chuggle away in the background on its own. This is just like my other videos showing how accurate the motor is. The Hall sensor I've also done a video on, showing how we can read this just like a switch. The Pico LED library I've used in other projects too, and in my Udemy Pico microprojects course. Check them out for an in-depth guide to driving these LEDs in more exciting ways than I'm using in this video too. I'm going to configure the LED's colour using HSV format, which is supported by the Pico LED library. This is the first time for me that I'm doing this. I normally work in RGB, but for illumination it makes much more sense to select the hue and the saturation. The switches I'm using are to start, stop, rotate and reset the controls for our turntable. They are using the internal pull-up resistor bank and read using interrupts. The rotary encoder needs to be read using a polling strategy due to the high amount of noise this device makes, so there is a FreeRTOS task managing this device. I talk a lot more about switches and rotary encoders in the Pico microprojects course. Finally, the OLED screen is an I2C interface device. There's a nice little library by -R that we can use to control this device. I've placed all of the source code, schematics, PCB design and 3D models into a library on GitHub. This is all open sourced under MIT license, so have a play and let me know how you get on. You've already seen a lot of the output from using this turntable throughout this video, but let me show you it in full operation. Using the rotary encoder, we can navigate through the menu. I'm going to turn the saturation up so we can clearly see the hue changing on the LEDs. The camera tends to see the LEDs as close to white unless the saturation is maxed out. Now let's cycle through the hues. The first thing the turntable does when it turns on is calibrate. It finds the start position using the Hall sensor, then counts how many steps in a full rotation. Switch 3 starts continuous rotation. A short press is clockwise, a longer press is counterclockwise. I use switch 2 to stop in between. I can also program the turntable to move at maximum speed to a start position and then moved in a defined direction at a defined speed to an end position, ideal for repeated recording of the same rotation. This is on switch 1. And finally, switch 4 is my reset by moving the turntable back to the home position by the shortest route. I think this was a fun little project that's really not difficult to build and develop. This builds nicely from some of my other YouTube videos and some background support from my Udemy courses. There are a few things I've learned from the project that I'll try to resolve in the next version. There's a little riding up going on between the cogs and I probably should have used a herringbone gear style, or used a bevel gear and changed the orientation of the motor. The Hall sensor detects the magnet over a fairly large number of steps, about 5 degrees of rotation on the turntable. This creates a dead spot in position selection. It's okay, but not perfect. I have some plans for Mark 2, and stay tuned to see me try these out. Remember to hit like and subscribe so you get notified of future videos. Let me know what you thought of the video or how you would design a better turntable.